And I will also keep on checking. If anyone puts their hand up, I will give them some space. So please do either way, either on Slack or just you put your hand up on the with the reaction button. So either way, I think on Slack I can already see some questions for Diego. One was already answered. So Rob, I'm happy if you want to make another comment about this, because I think that the binary are important. But if you are satisfied with the reply, but I think if you want to say something, Rob, I'll be happy for you to do that. I'll give you 10 seconds to.
No, I could.
Okay, great. Yes.
How you doing? It's nice to see you. And, you know, I'd really like to couple some kind of dust formation code to the yields that we make. And of course, we can do this statistically now. Well, we have been able to for a while. So it would be really wonderful to do proper population studies, actual numbers of stars producing this many grains. And that would be fantastic, because we're trying to do that for novae as well. But I'd love to couple that to some AGB type ejector. That would be really fantastic. I did get some responses online. I'm trying to type the response to that at the same time. So it's
okay. I also think this is an open question that we really have to address. And I think we talk about this for a long time, and it hasn't happened yet. But I agree, we need to keep it on the list. And yeah, but okay, that's another comment that's very interesting from Janet. I think if you want to say something, because this is where we can connect the stardust grain from the meteorites to actually the observation of grains around the stars. So if you can make some more.
Hello.
Yeah. Yes.
Yes, I did. I worked on some Spitzer data for saccharized objects, and I've published a paper very recently on it. The main grains produced by the star were carbonaceous grains, because it was an oxygen poor and hydrogen poor atmosphere. Sorry, my main field is dust, not evolved stars. And in this paper, I was also finding the potential for silicon carbide to be seen in these very weak features between 6 and 7 microns. And there are 2 tiny peaks which can be seen in very large silicon carbide grains. When I say very large, these are the sort of micron size plus grains, the ones that the meteoriticists can actually see in their samples. Whereas there was space for them in the feature in the cold dust. Now, in the hot dust that the star was currently producing, more silicon carbide seemed to be needed to to model the data. But that feature is the standard one at about 12.3, 12.4 microns. And that one, you have to have nanometer sized grains in order to keep it optically thin. And so this is why in the interstellar medium, these silicon carbide grains have not been discovered. I think Whittet, way back in the 80s, presented a paper saying where was the silicon carbide, and it couldn't be seen. And I think it's potentially very interesting. The difficulty is that you need a very high sensitivity to get the spectral features, and also in something like saccharized object, they vary with time, and sometimes they will be opaque. This is more in the paper, but it's not all in the talk. But it's something that needs to be explored. And I would like to say that as somebody who was trained as an astronomer, but came in with some geophysics and geology background, if I want to know what dust model to make, I always ask a meteoriticist first to see if they're finding anything remotely like what I think I'm predicting. And I think it's been a problem that the 2 disciplines can't speak each other's languages. So they don't know what questions to ask.
Yes, I completely agree. And I think this was also one of the open questions in Diego's last slide. How can we actually understand? Because the problem so far is that the people always tell us we can see grains, we can make grains, but they're always 0.1 micrometer. While the grains that the people can see in the lab because they need to use large grains, otherwise they cannot measure them. They are 1 micrometers or more. So then there's always been this big gap. And if you don't mind to just maybe put a link in the Slack for your paper, so then we can keep it there and go and have a look. And yeah, that would be great. And then we can ask you more questions.
With the grain size issue, the issue is what? I think in terms of the astronomy, the answer, I'm currently going through the Spitzer archive, basically eyeballing every single spectrum. And I'm seeing lots of potentially refractory features that look like the ones in the laboratory data, but aren't identified, because the ones in the laboratory data are very, very subtle. And the ones in the observations are very, very subtle. And there were good reasons why astronomers didn't necessarily believe they were there. But when you've got a stable observatory, something like MIRI and something like MIRI on JWST, you've suddenly got the opportunity to be able to go and observe these things properly. And it's something that hasn't been, I've been out of science for 14 years having a family, and I've come back and I have been astonished at how little has been done in the interim, and how huge the data set is and the potential that could be found if people knew where to look.
Okay, thank you. Yes, we should exchange this information. Okay, so I can see there are questions from Patricia Whitelock. Yeah, I was also a bit part of the UCT field, the UV field. Maybe do you want to ask the question in person, so then we understand each other a bit more?
Yeah.
Okay. Hello.
Sorry, it's my typing. I just wondered how much processing the grains would go through after they left the star, from the UV field or other processes, both in terms, well, mostly in terms of size. Thank you.
Diego, do you have any comments, or shall I try to?
Yeah, you can, sure, no problem.
No, please, if you have, like, this is what I understand is that in any case, the stardust grains are very, very small part of meteorites, and they are a very, very small part also in the general medium, because they are mostly processed. They are destroyed by shocks, by UV radiation. So actually, most of the grains we see, they are made in the interstellar medium. They are not stardust. So then it's very difficult. I wonder, like, I am not an expert, but this is something I also always wondered, like how representative of the size, of the real size, are the grains that we eventually find in the meteorites that have survived all these processes. Like, would the small grains survive better, or the large grains survive better? I don't think anyone has done very detailed. It's quite difficult to follow the sizes. I think it's open in some sense, like they are definitely very strongly processed. And in fact, these grains, they have typical lifetime in the interstellar medium of just a few, maybe 100 million years is a typical, because they don't live longer than that. But then how exactly that works, I haven't seen very detailed studies. I don't know, Diego, if you...
So my gut feeling that they may be very different by the time they get here from when they leave the star is not unreasonable.
Yeah.
Thank you.
Unfortunately, I have the same feeling, and people, but yeah. Diego, I don't know if you want to say anything.
I completely agree.
Stop. There was other interesting comment from Jaco. Do you want to ask the question about the cosmic rays? And then Diego put some paper that, so then maybe we can make this explicit, this question and answer for everyone.
Yeah, so whether the cosmic rays could affect the isotopes, but Jago suggests, I think by that link, that it wouldn't do that much, or maybe that was just about the interstellar radiation field.
Seems that the majority of the grains should come from 300 million years before the sun formation, and so they have no time to be irradiated, basically.
So what I understand is that only elements like light elements and rare isotopes like neon-21 or helium-3, they can come up from exposure from cosmic radiation. And there are some uncertainty because this is a difficult process to model, but this is how people measure the age of the grain in the interstellar medium. They check how much neon-21 there is there, and they assume that it was produced by interaction of the cosmic rays with neon-20, for example, or something like that. And then they say, oh, this took as many rays, and so that took as many years. But yeah, it's not a typical thing that would change, say, the strontium isotopic composition or things like that that we use for nucleosynthesis, I think. There was another question from you, Jaco. I don't understand it exactly. Maybe you can mention it. Are large grain conglomerates from smaller grains?
Yeah, so what happens in molecular clouds is that grains grow. So they stick and grow mantles, but they probably also stick. So they grow. And they can be made up of grains that come from wildly different populations of stars. Some may have produced those grains 10 billion years ago, and others maybe 100 million years ago.
What I understand is that the stardust grains that we find, they are typically homogeneous things. We don't find that they are made of little grains. Like they even find 6 micrometer stuff that is homogeneous. It has its own composition when they can measure it in depth. They can measure how the variation in depth. But I agree, as I said before, that lots of these grains are destroyed in the interstellar medium. You reform grain after you mix everything, you lose the signature of the stellar origin. That's gone. And then you agglomerate things, but it's not stardust anymore. It's like interstellar dust, which has already a homogenized composition. The stardust itself is a very, very small amount. So yeah, I think you would expect that these grow and they are quite homogeneous because the gas mixes and the dust mixes and you lose the signature. That's how I would look at the question. And there's also another question from Janet for you, Jaco. Finding evidence for large silicates. Do any of the stellar models, okay, we published a paper in 2005, but it sank without trace. Maybe if you post it again here, we will resurrect because every shared feature has been backseat by people working. Okay, yes, if it's possible to share, that would be nice. Okay, do any of the stellar model produce standard solar isotope ratios? Thank you. How do we know that they are extrasolar? Well, the stellar model, this is very, very complicated question because we recognize these grains because they don't have solar system isotope ratios. So that's their main property, that they have like carbon isotope ratios twice solar or oxygen isotopic ratios 10 times different from solar. And that's the signature of the stellar nucleosynthesis. But then if we want to go in details, we have to look at each element, each isotope, and it's a very long story. I can post some, but also the plots that were shown by Diego, you can see the differences from solar, and some models are above solar, some models are similar to solar, and it's a long discussion, but the signature of the grains is that they are non-solar. I don't know if this helped, but we can keep discussing out of offline. I don't see
Thanks.
anyone raising hands, but I see a lot of Slack things. So I'll keep on looking at the Slack, but sometime I'll go and check the list of participants. Jaco is asking, no, Randa, okay, yes, to what extent we can measure photospheric isotopes? There's two questions for you, Randa. I think I will ask Carlos to ask the question directly, because there's someone who hasn't spoken yet and we'd like to hear his voice. So if you are there, Carlos. I'll give you 10 seconds to try the microphone. You can unmute yourself. So I don't know if you want to answer these, Randa. Do you take into account the rotational velocity in the analysis? Okay, the microphone doesn't work. Randa, do you want to answer this question?
Sorry, can you repeat? So the voice is cutting off.
Did you take into account the rotational velocity in the analysis?
No, I did not. No, we did not. No.
Okay. And Jaco was also asking, to what extent can we measure photospheric isotopes? Anyone has any comments on this?
I mean, so the problem is that, so even we try to obtain the different, in addition to metallicity, we try to get the different abundances, but we do not, so because of the many variables that we have, our spectral range is very small, so we cannot really get all the accurate abundances for other elements as well.
We can ask if there's probably some other spectroscopy experts here. My understanding is that it's almost impossible unless you have molecules, and then you can do the carbon, the nitrogen. It's hard, but people have done it. Oxygen, magnesium. Some people try to do barium and all those, but other people don't believe them. I don't know who to believe. If any spectroscopist here wants to make a comment, it's very welcome. In the meantime, there was a question from Joya as well. Joya, do you want to ask it yourself? Because I think it's better if people develop a little bit. Thanks.
Thank you, Maria. Yes, I was just wondering, I mean, being not really an expert in this field, like to what extent up to now have been people able to reproduce synthetically the silicates features in like similarly to what has been found in the meteorites?
Maybe Janet has some ideas about this.
I've lost my microphone. I've just found it. There have been a number of problems. Some of the problems were issues with the way the laboratory data were obtained. Some of them were a misunderstanding of the laboratory data. If you're talking about the glassy silicates, then they work quite nicely, but they tend to fit. If you've got a sort of rounded curve like you do for the 10 and 18 micron silicate features in a lot of interstellar environments, you can approximately fit them with glasses. I once, a long time ago, in fact, it was in my PhD thesis, just tried taking random crystalline silicates and trying, and ones in a meteorite. If you take an average of all the features in meteorites, they do blend in the 10 micron feature, but however, you can make the argument, well, you could make anything fit it, but this was without fitting. This was just sort of taking a random average. We were collecting laboratory data, then all my funding stopped. We now have the laboratory data. I've just published, I published the paper on pyroxenes last year, which has 18 of them. These are chain silicates, which are ones that people have considered a little bit, but people are very reluctant to cover mixed compositions. So they were keen on the magnesium-rich ones because in the far infrared, you were only seeing magnesium-rich silicates rather than ones with iron in them. some of that may be a temperature effect. There was another paper I produced which showed that the bands shifted at low temperatures in the far infrared. This new paper shows that it's composition that seems that shifts them. And in a very preliminary analysis, I've just looked at a random young stellar object and tried sticking pyroxene spectra next to it, and quite a lot of the features matched the way I predicted back then. So but there's potential there. The laboratory data are pretty much on the way. They're on, these are taken of particulates. So it's not done with me theory and all its derivatives, where people assume that assume a shape. You take reflectance data, you then model them mathematically and assume some sort of assume ellipsoids and things and prolate shapes and that sort of thing. And it works for glasses because you can smear out everything because the features are broad. With the crystalline features, historically, it shifted the bands. I'm not sure of the details because I've never done it. But with the data for particulates, these are taken with no embedding matrix. It's just the powder, or it can be a solid sample. And they're highly compressed, so there isn't internal scattering in the sample. And you can get quite nice laboratory data, and they actually match with the peaks in the observations. So the potential is there. It could have been done 10 or 15 years ago with this set of observations. However, the data were not available because this area of research wasn't funded. I think internationally it wasn't funded. So I would make a plug that I'd like a grant, please.
Okay, thank you.
Sorry to go on.
No, it's great. I will check your papers and I might be in touch. This is exactly
when I came back
to talk about this.
I tried to come back. What persuaded me to come back was I looked and thought, oh, JWST still hasn't been launched. No, I haven't heard anything about it. And I went and I started looking at the papers and I went and looked and said, what? They haven't done this yet. So I'm playing catch up, but I could catch up quite quickly.
Yeah. There are some questions to go back to the spectroscopy. Angela, do you want to ask the question directly? I think it's a bit nicer than just reading it out by me. No, okay. Okay, Randa, can you see the Slack in case I made some mistakes or you can hear me? Okay, can you see
yes, actually I was typing the answer, so now, okay, I can.
Ah, you were, no, I want to hear the answer. So there's the fact that does not show multiple population, did you expect to find them? The young 2 GHz Magellanic Cloud cluster, which are variation CN, are all more than, okay, so maybe you can answer these.
Yes. So as I mentioned, yes, the multiple stellar population has been only observed in older star clusters, which are 2 gigayears or older. But because it's still not well understood why this is only observed in older star clusters, so that's why many groups are still trying to check in younger clusters if this is observed. Because it could be just a limitation with observations. So we don't know exactly why it's only observed in older clusters, because if we think about it, we believe that young massive clusters are the younger generations of globular clusters. So basically they're formed the same way. So we expect to see this multiple stellar population in younger massive star clusters as well.
There is one more question for you. If you have any large amplitude variable AGB stars in the youngish clusters in the inner galaxy?
I am not sure. So we did not observe any, no.
Okay. And I have another question about this, because maybe I didn't understand exactly, or because you are observing high mass stars, correct?
Yes,
red
yes.
supergiants, yes.
Yes.
So, but what I understand is that the multiple populations are seen in low mass stars because there is some idea that some massive stars evolved and then another group of stars was born. This is what people, so I wouldn't even, I'm not sure if I would expect to see variation in the massive stars, because there's the one to be born, they're the first population, and it's the fact that they evolve, and after we have a second group of stars that form So I am not sure that your results really rule out that these clusters eventually might also become, am I understanding?
Yeah, so this is this is true, but the reason we check this is because so the origin of the multiple cell population is not still clear. So one of the scenarios that was proposed to explain this is, as you said, that the first generation of stars have died, and then the ejection that came out of these stars formed the second generation. But this is not really confirmed. So there are many problems with this scenario. So that's why because we are not sure that this is the correct scenario, we are still checking in different star clusters to try to put more constraints.
Okay, so if you see this variation in these high mass stars, that would be groundbreaking.
Yeah, exactly. That's why we're hoping.
It's not just a question. Yeah. So okay, let's see. Maybe Okay, I understand. Let me check if there's anyone putting their hands up. I don't see anyone putting their hands up, and I don't see any more questions. But we have another 6 minutes because we can go until 6 o'clock my time. I don't know what other people's time is. So if anyone has any other questions, I have many more questions, but I don't want to monopolize the situation. So I prefer if someone else. Ooh, Jaco is asking a question. Very low metallicity stars affected by single supernova. Do we see that in isotopes? My understanding is that people have tried to observe barium isotopes, samarium isotopes, the europium isotopes in very low ion over H stars. Also to see if it was early S process or R process. And these are the papers that I can send some links, and I always hear people who believe or not believe this kind of isotopic determination. Actually, you cannot see, for the barium, for example, you can see the odd even ratio isotopes. You cannot distinguish each of them, but you can see the sum of the odd isotopes that are S process and the sum of the even isotopes and try to see the ratio, but then the error bar is so large that it covers everything. And please, Jaco, go.
Yeah, so the reason I ask is not because, although it is, these stars can be used to learn about those supernovae, but I'm just wondering whether stars care about the isotopic ratios they're born with. Does that do anything to the ensuing nucleosynthesis, other processes at all? Or is that erased?
Well, this is very interesting, very complicated, because generally speaking, the star, like for the silicon carbide grains, this is very interesting because anything that is produced in AGB stars, so strontium, yttrium, zirconium, barium, you don't feel the initial composition because everything is reset to the S process made in the stars. There's a lot of S process you don't see anymore, it's just hidden. But for silicon, for example, we observe, of course, these are silicon grains, so we have a lot of silicon data, and that shows the initial composition of the star, because the neutron captures in AGB stars don't change the silicon very much. I mean, this is again another big topic. So in that case, we can see the initial composition, and in that case, it matters, but it won't matter for the star itself, doesn't care. We care because we can observe silicon in the silicon carbide grains, and we want to try to explain it. But if the star itself is born with different silicon isotopes, I don't think it would impact at all the evolution or the nucleosynthesis, but we would have to consider it when we compare to the data. I don't know if that's clarifying or confusing the question. But we have 3 minutes left. Well, we can also keep on going a bit over time, but maybe it's getting late, and I don't see any questions. I don't see any hands. Maybe you want to say a few words to close? Jaco or Joya, if you want to.
Yeah, fine. Thanks, everybody. I've stopped the recording, but I think Joya is still recording as well. Thank